Go. Hello and welcome to Calculus. So, introduction to calculus, pre-calculus tricks and things we are going to need. First off, I'm going to see if you could invest and find a square notebook. We are going to have a lot of graphs in this class. Reading the graph is extremely important. Graphing is essential to calculus, and in order to have proper graphs, you need to have divisions on x and the y-axis equally. So investing in a square notebook, and you see me working on a square grid all the time. Lined paper is not good because it doesn't give you the equal divisions vertically and horizontally, so the graphs come out crooked and then you don't learn from them. So what is calculus? Calculus is a study of change in nutshell. So, oh, my pen, come on. All right. Come on, pen, wake up. Come on, calculus is a study of change. And obviously motion is going to be one of the big deals that we will talk about. Just if the pen decides to work now. Give me a sec. There we go. So, calculus is a study of change. We have body weight, and we are the lightest for the day when we wake up in the morning, and we are the heaviest before going to sleep, because we have the food intake throughout the day and we just don't do anything, right? Now, the height works differently. You are tallest in the morning when you wake up because you were passed out horizontally, right? Your joints, everything expanded. And then you get up and then all of your joints get this weight, and throughout the day, everything compresses. So some fraction of an inch, you are shorter by the end of the day, and then you're going to pass out again and everything is going to stretch and you go. Those small changes can be noted. When you drive, you will be using the fuel in your car engine. The whole system, which is the car plus you, will be losing weight as you are using up gas in your gas tank as you are going from point A to point B. So a lot of these systems outside everywhere are changing and evolving in time, and calculus is there to measure. You also change your distance in time. Distance is measured in miles. Time is measured in hours. So how fast are you changing your distance per time, right? We say speed, velocity. We will talk about these concepts. There is a whole section for it coming up in chapter 4. So, or 3. So we are going to discuss a lot of these things, and calculus gives rise to all of our engineering and physics and advanced economics, and pretty much all aspects of our life are touched somehow by calculus, which is why it's required for pretty much everything. So calculus will consist from 3 different concepts: limits, derivatives, and integrals. So we are going to have 3 limits, derivatives, and integrals. Now, let's split this way. Limits are going to be in chapter 2, and limits are going to be, I like to say in a nutshell, a fancy way to compute the y value of the function. So limits compute y values of the function, and we'll have a notation limit of f of x as x goes to, let's say, a is equal to L. Now we're going to toss in infinities and all other cool stuff when we get there. Derivatives, chapter 3 and 4, will cover the change. So derivatives measure change. And the notation f prime of x, and we'll use, I'll put dy dx, and we'll understand the notation on all of these things. So derivatives measure change. And finally, integrals. For us, only chapter 5. You will continue with integration heavily in chapters 6 and 7 and 8 in your Calculus 2. This is just the most important stuff. Only 5 sections of integration in Calc 1. And that covers the accumulation. So integrals compute accumulation of stuff. So you can use them to calculate areas. You can use them to calculate energy. We'll see all different applications when we get there. So that they measure work. There's just so much that you can get with calculus. So calculus integrals. So they integrals compute accumulation. So it's addition, it's summation, and all of that stuff. We'll have integral of f of x dx. So these are the components of calculus. Now, the most important part here is to note that each one of these has the f of x present. So I'll write this now over here in blood. Calculus is performed on functions. There are certain non-function situations where you can, do things with calculus, but for the most of our application here, it's functions that calculus is applied on. So now that begs to go back to PreKalk and say, what is a function, right? And that will be a question on your first exam for 4 points. And you either write it for 4 points or mess it up in any way for 0 points, right? Deal. I told you the question on the first exam. What is the function? Or write the definition of a function, whatever way I phrase it. You are going to have that question on your first test. Let's go. Function is a rule which assigns to each x in the domain a unique, no coughing, y in the range. And now we underline words. Rule, domain, range, and the word unique underlined twice. That's the one that makes this work. Now we explain those words. Let's go green. Rule refers to a formula. F of x equals x squared plus 3. So you have some formula. It could be e to the x minus 1, it could be sine x over 2. Some formula is there. That's the rule. The rule that you are going to use to compute the values. Domain. Set of all possible input values. Range. Set of all output values. Y is a consequence of x and the function. Now, when I say, and you look at the two definitions, domain and range, there's only one word that is different. And that word has to be there. Because you are only allowed to plug in values into a function that makes sense, or that you can. That's why we call it a domain. Set of all possible values that you are allowed to use. Square root of x function. You are not allowed to use negative numbers because they create complex numbers as the result, right? In a function 1 over x plus 3, you are excluding what? Negative 3, thank you. Because negative 3 would make the whole thing explode. Can't divide by 0. No, that's literally explode. Explosion. And we'll see why. When we get to chapter 2, I will give you the answer to that. So we have the word possible there because for certain functions you are not allowed to plug in certain numbers. So the word possible needs to be there. And finally, we had the word unique. Now, this simply means that each x must have only one y. It's like in that movie Highlander, there can be only one. I don't know if you've seen that. You definitely have. So I need you to think a little bit about functions and the word unique. The light switch is all the way there, and that light switch has a function to control the lights in this room. Now, it's its function. What is in the domain of the switch? Meaning, what are the ways that you can excite that switch? Finger, right? Palm of the hand, your nose, someone else's nose, right? There are ways, right, that you can excite that switch to toggle the lights on and off. So you have input, which is whatever. There are things that are not there in that input. Those are the ones that are not in the domain. Give me an example of something we can't use.
Someone screaming.
I'm sorry?
Someone screaming.
Screaming
at the lights.
Or you scream at the light switch? Great. This is a mechanical light switch, so screaming at it won't work. Voice-activated one would, right?
Yes.
Which gives me actually, because I do have, I am going to, yeah, oh man, that's my project for tonight when I get home. Next time, starting tomorrow, when I walk into the room, I have to go, wah! to turn the lights on. All right, good. That's going to be rewired tonight. Thank you. Students came up with Jello. You can, use Jello because it's just going to go everywhere. I came up with the moon, right? The moon orbits the Earth. They did shrunk the moon in one of those cartoons, right, and stuff like it. Trust me, it doesn't work. It will still be the same mass. You can't lift it. So even if you shrunk it, it's not going to work. So that's what the function is now. Think of the light switch. Think of other things in life that surround you. And you think, okay, what are all the things that can excite the system? That's the domain. Think of some absurd things that cannot excite the system. That's outside of the domain. The output of the whole thing is the outcome. So lights on, lights off, in our case. The rule is that that switch controls these lights by pushing it. I don't have to worry about causing an earthquake somewhere by pressing that button there. We can wire that. Tesla did, right? But let's not. And uniqueness. Now the word unique means that switch controls these lights. When you push that switch, these lights go on and off. Not the lights in the hallway, not the lights in the other building. Once you wire it, that is its function, and that is unique function. To understand all of these again in now mathematical setting, right? The boring one, we have f of x is equal to 2x plus 3. Now, if I calculate f of 5, that would be 2 times 5 plus 3 to give me the output of 13. Now, I have an ordered pair, 5, 13, as input, output. I can graph this. I can graph other points and connect them with a line and call it a graph. So, for a function like this, domain would be all real numbers. In your pre-calculus course, you either use the double bar R or you use negative infinity to positive infinity. I don't care which one you use. Range is, again, in this case, all real numbers. Double bar R. Rule is the formula itself. And then, no matter who, this classroom, outside the classroom, in a galaxy universe, doesn't matter. Whoever plugs the 5 into this formula must get 13. This 13 is the unique answer for 5 being plugged in. Otherwise, it's not a function. So it's the word unique that makes the entire definition work as a function. If you remove the word unique, you get a broader concept that is called relation. Now, not everything in life is a function. You are looking at one right now. What is the input for this tablet? This, right? How many outputs do I have? At least 3 right now. 1 that I see. 2 that you see. Is there one on YouTube as well? Uh-huh. It's streamed live right now. You might have, stayed home and you are watching this live from your home or Starbucks or somewhere, whatever. So, that is not a function because a single input has 3 outputs. You see that? So, are non-functional allowed in the world? Clearly, yes. Do we do calculus on them? For most part, no. Right? So, you cannot say, not a function, we are not interested. No. We are interested if it's a function because we can perform calculus nicely and easily. Otherwise, it's hell on earth. Other courses are coming up where you will have to deal with that. And we'll have few little things here and there, not functions. We'll deal with those. But for most part in calculus, we want to have a function because calculus goes smoothly with those. What types of function are you expected to know walking into calculus course? What types of functions you are supposed to be able to work with out of the box, let's say. So, number one, polynomials. Polynomials, let's say p of x, a0 plus a1x plus a2x squared plus a3x to the 3 plus dot 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 plus an x to the n as the leading term, the one with the highest exponent. So if you keep this much, say y equals to 2, it becomes your constant function at 2, horizontal line. It's a polynomial. Y equals to 2 is in that family. If you use first two terms, you have your linear lines, y equal mx plus b. Your m is a1, your b is a0. So all of your linear lines are also part of the polynomial family. Clearly, the next one is quadratic, with your ax squared plus bx plus c, quadratic formulas and all of that stuff that you know from your previous courses. And then you have the cubic, and as far as this one would go. You have to have the highest degree, and that one is going to be the degree of your polynomial. That's going to be your leading term. Very important for courses that are coming. I mean, lectures. Number two, exponential functions. You will be sick of exponential function e to the x by the time you're done with Calc 1, 2, and 3. For a reason. It's the easiest one to differentiate and integrate. Those of you with experience already in calculus from high school or previous courses, you know that derivative of e to the x is itself e to the x. An integral of e to the x is itself e to the x. So we use it a lot because it's cheap and easy and quick. Plus, e to the x has a monopoly on nature, right? Pretty much every aspect of our life has e to the x in some way or form. So we will be using a lot of e to the x. So we're looking at y equals a b to the x as a general form, but in particular, e to the ax is what we care about the most. Number three, this is like a popularity contest, like what is, most popular. Number three would be the rational functions, the one with the square roots. Sorry, radical functions. So radical functions, y equals nth root of some function. Clearly, we have square root of x, y equal, cube root of x, and stuff like that. Then we have the rational. Rational function, y equal a function divided by a function. Mainly polynomials, but you could have other stuff as well. So f of x divided by g of x, give you an example of 1 over x is the cheapest you can go. But then you can have, x squared plus 1 divided by 3x minus 7, whatever. Number 5, trig. You got 6 of those: sine, cosine, tangent, cotangent, secant, and cosecant. So trig, I'll just put all 6. Logarithmic function. The coolest and the most powerful differentiation technique will ask you to use logarithmic differentiation. By far the coolest thing in, I think, all Calc1. But in order to do it, you should be able to deal with logarithmic functions from PreKalk. So logarithmic function, y equals log b of x. Primarily we focus on ln x, because that's the inverse of e to the x. 7 piecewise functions. Oh, absolute value. Y equals absolute f of x. Example is y equals x, but that's lame example. Absolute x, I mean, there are much better examples as we go along. 8 piecewise functions. And those are the ones that have pieces to it, hence the name. So let's say you have x plus 1 for all x is less than -2. Then you have function equals to 3 for all x is in between -2 and 6. And then you have x squared plus 1 for all x is bigger than 6. So generally, you freak out when you see that. That's all just 3 functions in one. And each function is active at a different part of the domain. And which part? That's given right there. So, if I want to graph this, which is the next part, graphing. If I want to graph this, I would graph each piece on its domain. So this is where the square notebook comes in. So I see a barrier at -2. I'm going to draw orange barriers and then delete them later. 1, 2, 3, 4, 5, 6. So these are my barriers. X and y. And now I draw these functions. The cheapest one is 3, obviously, that's in the middle. I use the closed circles on both ends. It goes through 3, it's horizontal line. And it's between -2 and 6. Then I have x plus 1. X plus 1 is a 45-degree line that goes through 1. Yeah. But I am not allowed to have this part of the function here, because x plus 1 is allowed. No, I lied. This is bad. I have it backwards. The slope is positive. Supposed to look like this. There we go, much better. So I'm not allowed to have this part here. None of this. Because that's where the tree lives. So I am only allowed to have this part of the function. That's it. The rest has to go. Bye-bye. Okay, that's that. And finally, the one that I can't draw is the x squared plus 1, because x squared plus 1 is going to grow too fast, and it's out of bounds for my drawing here, but x plus 1 would have so 0, 1, 2, 3, 4, and then for 6, that's going to be really, really high up. So it's going to be a piece, open piece, and then go like that all the way out there somewhere. So as you can see, there are 3 parts of the function. Now you erase these construction lines, the orange ones, and here's your piecewise function. You have the first piece in effect before it hits x hits negative 2. That's the linear part. As soon as x hits negative 2, the next piece of the function is in effect. And as soon as that hits 6, it stops for that line, and this function takes over wherever it starts, right? You always, well, I mean, 6 squared is 36 plus 1 is 37. So y is 37. This is 37, right? That's why it can't fit on the graph. So, and then it goes from there. Being able to graph these functions, since the class is over, I'm just going to mention absolute value, and that's it. So y equal absolute x, you probably all memorized that that's a v-shape function, 45 degrees this way. But now that's not going to be good enough for our calculus here, because the next one is absolute value of sine x. Now, right? So we don't want to memorize absolute value of x as a v function at 45 degrees. We want to learn the proper way to get that function so that we can get every single other function that shows up within absolute value. So the way to do this efficiently is to say, all right, let me graph y equals x. Just forget about absolute value. And that is going to be a 45-degree line like this. Now, what we know is that the absolute value, right, because it measures the distance, and distance is never negative, absolute value is not going to allow for negative y values. So we are supposed to reflect this one up in the positive quadrant. So this point goes there, this point goes there, this point goes there, and we get this piece, which is absolute value of x. So now, when you are faced with sine x, you will take a look at y equals sine x without absolute value, which is going to be the little wave, which would immediately mean that this bump needs to go up into the positive region. So this graph would be your sine x absolute value, where both graphs. So now you are learning that for absolute value graphs, you are not allowed to have anything below x-axis, and whatever is below, you have to reflect it up on the other side. So what are you going to graph when you get home to practice this? Well, obviously, absolute value of ln x. That's for you to graph when you get home and add to this list. Bye. What's sorry?
Absolute value of what?
Of ln x.